Section 4.5.1 Chained Digit Generator. Let me end this section with a simple pseudo-random number generator that can easily be done using paper and pencil. No computer required. Let's call it the Chained Digit Generator. Begin by writing any 7-digit decimal number. These 7 digits are called the seed or initial value or initialization vector. They can be considered the key or a part of the key for any cipher that incorporates this generator. To get the first pseudo-random digit, you simply add the first and last digits. You append this new digit to the sequence and black out the first digit. So, starting with 3920516, we add 3 plus 6 to get 9. Anytime the sum exceeds 9, we drop the tens digit. That is, the addition is done modulo 10. This is sometimes called non-carrying addition. To get the second pseudo-random digit, we repeat the process. Here, 9 plus 9 gives 18. We drop the tens digit to get 8. This process can be repeated to get as many pseudo-random decimal digits as desired. The resulting pseudo-random sequence is 9800562199940232. Notice that if all of the digits in the seed are even, then all of the generated digits will be even. Likewise, if all of the digits are divisible by 5, namely 0 or 5, then all of the generated digits will be divisible by 5. In that case, the period could be no more than 128, since there are 7 digits in the seed, and there are only 2 to the power 7 equals 128 possible combinations of zeros and 5s. Since such seeds cannot produce long periods, they are called unqualified. For the chained digit generator, a qualified seed must contain at least one odd digit and one digit that is not a multiple of 5. For example, 2222225 is a qualified seed, but 2222222 and 5555555 are not qualified. With a qualified 7-digit seed, the period will always be 2,480,437. This generator has behavior typical of homemade pseudo-random number generators. There are 10 to the power 7 possible 7-digit seeds. If you start with any seed, the generator will cycle through some sequence of numbers until it produces that seed again. So the set of 7-digit numbers is partitioned into several discrete cycles, each with its own period. If you choose a qualified seed, then the cycle will always have the maximum possible period of 2,480,437 numbers. There are 4 separate cycles of this length, plus several much shorter cycles produced by the unqualified seeds. The behavior is similar for seeds of other sizes. Even when the maximal cycle is very short, there is often a high probability of getting a maximal cycle because there can be many maximal cycles. This table shows the probability of getting a cycle of a given length using a qualified seed. The table shows that seed lengths of 5 and 8 digits are not safe. They produce a large percentage of very short cycles. Seed lengths of 7 and 10 digits are best because you are always guaranteed a long period. This random number generator is strictly a demo model, just to show you what can be achieved using simple hand methods. It is not suitable for high security work. Section 4.6 Useful combinations, wasteful combinations. The 4 basic techniques of this chapter can be used in myriad combinations, which I explore throughout the remainder of this book. However, it is important to recognize right at the outset that not every combination is beneficial. Some combinations add work without adding strength. Consider an idea that some beginners try. They perform a simple substitution on a message, then a second simple substitution on the resulting text, then a third, and so forth, for 5, 10, even 100 rounds. This is a waste of effort. Performing 2 simple substitutions is the same as performing 1, but with a different mixed alphabet, so performing many simple substitutions does not add any strength. Here is an illustration. The 2 substitutions are mixed with the keys first and second. The third substitution is equivalent to performing the first followed by the second. Let's try an example. If we encipher the word example using the first substitution, the result is IUXEJDI. If IUXEJDI is enciphered with the second substitution, the result is CLQYOXC. You can verify for yourself that enciphering example with the equivalent substitution yields CLQYOXC. Performing one encipherment and then a second encipherment is called composing the 2 encipherments. The previous example shows that composing 2 simple substitutions just produces another simple substitution. If the first encryption uses a code, then following the code with a cipher is called super-encipherment. The most common form of super-encipherment is non-carrying addition, or addition modulo 10, which works like this. Section 4.6.1 Bazary Type 4 Cipher. Let's look at the opposite case. Let's look at a cipher where using a substitution step followed by a very simple transposition produces a cipher that is much stronger. The cipher was proposed by the brilliant, irascible and vituperative French cryptographer Etienne Bazary in 1898. I do not know what Bazary named this cipher. I call it Bazary Type 4 because it was the last of 4 ciphers that he proposed to the diplomatic Bureau des Chiffres during the 1890s. It can easily be done by hand. The Bazary Type 4 consists of a simple substitution followed by a simple transposition, which I call a piecewise reversal. The transposition reverses short pieces of the text according to a key that is a sequence of small integers. Here is an example using the keyword BAZERIS to mix the substitution alphabet, and the key 423 for the transposition. This type of transposition can be used to strengthen many different types of ciphers, so it deserves a name of its own. Let's call it piecewise reversal. You can strengthen this transposition by mixing in a few segments of text in normal order, perhaps by using negative numbers in the numeric key. Here is an example using the numeric key 3, 4, -3, 2. Note that this key is equivalent to 3, 4, 1, 1, 1, 2. The cryptographers at the Bureau des Chiffres were unable to solve any of the sample messages that Bazary provided. Despite considerable effort, the messages remained unsolved for 40 years, until renowned architect and amateur cryptographer Rosario Candela solved them and wrote a book about how he did it, The Military Cipher of Commandant Bazary. Candela, however, was unable to decrypt the messages directly. Instead, he identified and exploited a weakness in the way Bazary generated the substitution alphabet from a key. If Bazary had used a stronger method for mixing the cipher alphabet, Candela could not have deciphered the messages. Consequently, Bazary Type 4 with a well-mixed alphabet is rated 5. Pretty good for combining 2 methods that are each rated 1. Historical tidbit. Candela was a graduate of Columbia School of Architecture, so he planned to publish his book at Columbia University Press. William F. Friedman, then the Dean of American Cryptologists, got wind of this and secretly blocked the publication. This again attests to the strength of the Bazary Type 4 cipher.